Welcome to the workshop. Today we want to take a look at section 8.2, which is confidence intervals for one population mean when the standard deviation of the population mean is known. Now, what kind of situations are we actually going to know the population standard deviation where we don't know the population mean? After all, isn't the standard deviation calculated using the mean? Well, yeah, so the reality of this situation working out super well for us, doesn't really happen. But in the next section, 8.3, we'll look at confidence intervals for one population mean when the standard deviation is not known. So we'll get into that in the next section. For now, we're trying to keep our computations a little bit simple, work with things that we're already familiar with. And in the next section, we'll introduce what we need to be able to work with the standard deviation not being known. So let's take a look at our notes. So again, section 8.2 is confidence intervals for one population mean when the standard deviation is known. Now here it says also one population mean, and that's because it is possible to also consider two population means, which this textbook does discuss, but we will not look at that content. So we're just worried about estimating a population mean. Okay, that's what we're trying to do here. In particular, using confidence intervals or creating a confidence interval estimate. So we want to take our conversation from the previous section and make it a little bit more rigorous, make it a little bit more specific, make sure the details are all there. So in the previous section, let's actually go back to that a moment, see if we can find it. We looked at a normal distribution here and said, hey, look, if the mean is here, we're 95% confident, right? 95% of the time, the mean of a sample is going to lie within about 2 standard deviations, according to the empirical rule. All right, but the empirical rule says approximately 95%, and we can be a little bit more specific than that. So what we want to do is we want to say, well, 2 things. Instead of saying, looking at the known mean, we would say that the sample means lie within 2 standard deviations of it, right? And in the last section, we said, well, we can in turn say that if we find a sample mean, that then the population standard deviation lies within 2 standard deviations of, sorry, the population mean lies within 2 standard deviations of that sample mean. So what we're going to do is we're going to change our picture to be where it's centered about the sample means, because that's what we're using as our estimate here. So what we're going to do is we're going to construct what we'll call a 95% confidence interval. That percentage can change, but it's what that's the one we'll use for now. We'll look at examples a little bit later where we're using something different. So if we're looking at a 95% confidence, what we're saying in that is that we want to be correct 95% of the time. If we're correct 100% of the time, we've got to make that interval way too big. It won't really be a reasonable estimate. So we want to say 95% confidence. So get this area here to be 95 hundredths. Excellent. That means that this area over here, right, and that area over there are equal because we're looking for that centered 95%. And the areas there would be 0.05 divided by 2, which is 0.025. Yep, there we go, 0.025. And I don't know what this value is here, but it's going to be adding about 2 standard deviations. We'll figure out what that is here in just a minute. But in order for us to find out what those are, it'd probably be easiest to use the standardized normal distribution and then bring those z values up to here, essentially is what we're going to find. But a couple of comments before we do that. Let's see here. The numbers that we find here and here, right, this are going to be given by the mean plus some error and minus some error. So this is going to be x bar minus some error and x bar plus some error, where this distance here is the error, okay? So that's what we want to find. and E is called the margin of error. And we'll look at that a little bit later, and it changes based on our confidence level because that changes those values here. But let's say we have the standard normal distribution. So I've got a second image here. Let's see, click here. There we go. So right there and right here. Right there. Okay, so 0. We want this to be 0.95, and we want to find this z value and this z value. But this right here is 0.025, so what I'm looking for is z sub 0.025. For us to find that z value, we use table 2 from the appendix. So we take 1 minus 0.025, and that gives us 0.975, and we find the z value that has that area to the left. So that's the area to the right. This is the area to the left. And we go to table 2 of the text, and we look for that area. So I say, all right, well, these are all less than half. These are all above half. So I'm going to zoom in on this stuff over here. And I look for 0.975, 973, 974, 975. That's the value that I want right there. So it's 1.9, and I go up to find the hundredths place. So it's 1.96. Excellent. So I come over here, and I get that this is z sub 0.025 is 1.96. So we said about 2 standard deviations, or we said within 2 standard deviations is about 95%. So the reality is if we want exactly 95%, it's 1.96, not 2. So we go back to here, and we say that this is x bar plus, actually, let's get rid, well, leave that there, I guess. So x bar plus our error. And what is our error? Well, I suppose in order to find that, we would actually have to recognize how we find z values. So z is equal to the observation minus the mean divided by the standard deviation. In this case, we're using the standard deviation of of the sample means. So the standard deviation of the sample means is standard deviation of the population divided by square root n. So if I wanted to find that x value, all right, that's not so bad. I multiply both sides by the standard deviation, so I get, let's see here, z times standard deviation divided by square root n, population standard deviation, is equal to x minus x bar. And then, of course, add x bar on both sides to get x bar plus z times standard deviation divided by square root n is equal to x. And in this case, what we're actually looking at for each of these is z sub that number over, that special number, this special number. But what we do is we express our confidence levels as 1 minus alpha, which means that the area here, right, alpha over 2, alpha is 0.05, so this is alpha over 2. So these z values are expressed as alpha over 2. So this is x bar plus, in our case, 1.96 times the standard deviation divided by square root n, and that is the error. And the error over here is the same thing. We're just subtracting it, 1.96 standard deviation divided by square root n. So this is very formally, right? This is how we calculate our error. Our error is, in general, it is the z value, right? This value here. How do we get what it is in our data set? We solved that. And that specifies what our error is. Okay, that is our error. The alpha value is the right. If we want to be 95% confident, that gives us alpha is 0.05, the area in the tails on either side. And right? Or the tails on either side together. So we split it in half to get alpha over 2 is the area to the right. So z sub alpha over 2. So our area is z sub alpha over 2 times the standard deviation of the population divided by the square root of the sample size. And that's just the standard deviation of the distribution of the sample means, right? Standard deviation of the sample means. Okay, so we'll bring that along as we complete our examples, and we'll see that again a little bit later in the section. And I think that that's all that we wanted to do here. But our statement from the previous section that the sample means, all right, 95% of the sample means lie within 2 standard deviations of the population standard. The sample means, 95% of the sample means lie within 2 standard deviations of the population mean. Yes, here, focusing on what our sample mean was, we would say that we're 95% confident, or 95% of the time, the population mean is going to lie within 1.96 standard deviations of this particular or of the sample mean. And so when we look at it as a specific instance, we are 95% confident. Okay. If we were to repeat it many, many times, we'd be correct 95% of the time. 95% of the time, the population mean would actually be within those confidence intervals. So when we're looking at one specific instance, we call it 95% confidence. All right. So that's quite a bit of conversation about how we look at how we develop a confidence interval. All that remains for this section is just some observations. So really quickly, we no longer use -2 and 2 because we can look at z sub alpha over 2, and we've specified that if we want actually 95%, it's 1.96. So we'll use that z value instead of 2. We're improving that approximation for this section. This is the outline of a procedure that we can use to find our confidence interval estimate. It requires that these assumptions are satisfied. We'll look at those as we complete our examples. Feel free to pause the video and read over it now. But what we need to know is we need to know that alpha value. So we need to know the confidence level and the alpha value. And then we can compute the error and subtract it and add it to find the numerical representation of our confidence interval. And once we've done that, we can interpret our confidence interval. So it's some assumptions, 3 assumptions, and then 3 steps. Pretty simple. And it really is that simple. And then we have a bunch of, well, actually here, this table will be used. It gives us some of the z values. But then we also want to know, when is it appropriate to actually use this procedure? When can we use procedure 8.1? Well, when we have a large sample, we're pretty much good to go. Or when we know that the population is normally distributed, right? The variable is normally distributed. But we also need to know that there are no outliers. So for small samples of less than 15, we have to have that the variable under consideration is normally distributed, and of course, no outliers. Although it's kind of hard to identify an outlier when there's only 15 observations. If we have a sample of moderate size between 15 and 30, again, there has to be no outliers, and it has to be normally distributed. Has to be, otherwise we can't use it. Or very close to normally distributed. For large samples, we still don't want any outliers. So if we can't remove the outliers, the best thing to do is actually to perform the procedure with the outliers, and then perform the procedure without the outliers, and then compare the 2 things to see what we get. But if there are no outliers and or their removal is justified, then we're good to go, take them away, and do the procedure. So we want to keep this in mind as we perform that as well. All right, but of course, we want to respond to these things before we actually perform the procedure. So if we were to ignore these guidelines and we were to ignore these assumptions, then it would not be appropriate to apply these procedures. You'll find that in your statistical project, you're going to have to pay attention to these assumptions and you're going to have to pay attention to these guidelines, but it won't actually satisfy some of them. And giving recognition to them, you will also want to continue on and still perform the procedure, just saying, hey, this isn't going to be the best thing ever because we don't actually know for sure that this is really ideal, right? We don't know for sure because it doesn't satisfy all of the recommended requirements. So let's see, we'll take a look at this example during lecture. So quickly go through that. We already said what the margin of error is, which involves n. So we'll get to that in a minute as well. How does n impact it? How does the confidence level and alpha impact it? Well, if we increase our confidence, we have to have a bigger interval, because in order for me to be more confident, I've got to say, hey, I need a bigger interval to contain those other possible values that it might actually be. So increased confidence gives increased confidence interval. If we increase the sample size, we took a look at this back in chapter 7, where we talked about the heights of starting basketball players. If we increase the sample size, we got better approximations. So when we increase the sample size, we're actually going to get a smaller confidence interval estimate. Now, each of these things conceptually we've talked about, but we can talk about them mathematically as well. They're right here. If we increase our confidence, right, the z-value is going to get bigger, so it's increasing our error. If we increase the sample size, then this overall number here, this fraction, has a larger denominator, making its overall value smaller, decreasing our error. So we should see those relationships, and we'll investigate those in a couple of examples. Now we said that the error is given in terms of the z-value and in terms of the, let's see here, and in terms of the sample size. So I can solve for sample size in this, right? Divide both sides by the z-value, error divided by z sub alpha over 2 is equal to, oh, actually, you know what? That's not the way I wanted to go about this. Multiply both sides by square root n. There we go. Square root n times the error is equal to z sub alpha over 2 times the standard deviation. Now divide by the error to get square root n is equal to z sub alpha over 2 times standard deviation divided by the error, and then square both sides to get n is equal to z sub alpha over 2 times the standard deviation divided by the error squared, which is exactly what they have here. Which means what for us? Well, if we know our confidence level and we know what error we desire and we know the population standard deviation, then we can plug those in and find what size sample is required for all of those things to be satisfied. Okay. In particular, if we want a specific error, we can find a specific n to make that happen. Okay, and we'll look at an example of that. But that's all that there is for this section. So thank you for your time and your attention in section 8.2. We'll look at the examples and discuss this a little bit further during lecture, but hopefully this really quick run through will make it a little bit easier for us to do that during lecture. So I'll see you guys again soon here in the workshop for section 8.3 as well, and then again in lecture. Have a great day.